Okay. A planet has a radius of 3.1 times 10 to the 6th meter. At point P, a distance of 2.4 times 10 to the 7th meters above the surface of the planet. The gravitational field strength is 2.2 newtons per kilogram. Calculate the gravitational potential at point P. Include an appropriate unit for your answer. Right? So the gravitational potential, of course, is going to be what? Joules per kilogram. Right? And when they say we write them joules per kilogram. I feel like they're going to want you to write it this way, right? Okay. Now, they just gave you a formula for finding the gravitational potential. And I, of course, didn't believe this formula, but, there it is, right? So V is minus G, and then it's the radius of the planet plus the height above the planet, right? Okay. So, literally, you could just plug this in, right, for that, right? The radius of the planet is there. You can plug that in, and then the height is this, right? And you can plug that in, and you get something that is about 6 times 10 to the 7th joules per kilogram, right? Okay, there it is. Now you can make that a lot harder. What I did was I said I did 2.2 is equal to gm over r squared, right? And r is the this plus this, right? Okay. Then I solved for the mass of the planet, and then I plugged it into this. V is minus gm over r, which of course gives exactly the same thing. But it's a lot more work, so I encourage you to do it that way, right? Okay. Then it says, it shows the asteroid, right? And the asteroid starts from very far away, right, at infinity, where it has, and it has a negligible speed, right? So this thing's starting from zero energy, right? Its initial energy is zero, right? And then that's going to equal the kinetic energy it's got, 1/2 mv squared, right? Plus the gravitational potential, which would be g mm over r. And this is how we solved it, right? But keep in mind that this thing right here, this is just our potential, which we figured out here, right? This potential is like 59.62 million joules per kilogram or something like that, right? Roughly 6 times 10 to the 7th negative joules per kilogram. So ultimately you can just do this, right? That it's that 0 equals 1/2 mv squared, right? Plus the potential that you figured out, which is negative already, right? Times the mass of the Earth, right? And or the mass of the asteroid, right? The asteroid mass will cancel, and so you end up with the velocity. You can just plug in here, right? The velocity squared will be twice that potential, right? And the opposite of it. I mean, make it positive, right? And then just square root. So this is velocity. This guy here is the gravitational potential that you figured out here, okay? All right. And I think, there's one more question, right? So then it says, the mass of the asteroid is 6.2 times 10 to the 12th kilograms. Calculate the gravitational force experienced by the planet when the asteroid is at point P, right? There's two ways to do this. The way I did it was, because I lacked imagination, was that I figured out the mass of the planet, right? And then I just used, because it's going to be g, mass of the planet, mass of the asteroid over r squared, right? Okay, so what I did was I figured out the mass of the planet, which we actually don't know. They don't tell us that ever, right? But you can figure it out from this. If 2.2 is equal to gm over r squared, right? And r is your 2.4 times 10 to the 7th plus 3.1 times 10 to the 6th from the previous page, right? And g is 6.67 times 10 to the minus 11th. You can figure out this mass. It ends up being like 2.422 times 10 to the 25th, right? That's a lot of work. So I figured out this mass, then I plugged it into this, and that's the force of gravity, right? But you know what? You can just do this, right? Can't you just say that the force of gravity is just mg? And where m is this, right? And then this is the 2.2, right? That's a whole lot easier, isn't it? Okay, then you're going to get an answer, which is, of course, the force that's exerted on the asteroid. Here's this little asteroid, right? That's the force that we just figured out. But of course, Newton's third law states that for every action, there's an equal and opposite reaction. And so these forces of attraction would be equal, right? I guess you need to say that, right? Newton's third law and then just mg. All right, good luck.